Hey everybody! Alright, so let's keep talking about waves. So this lesson we're going to talk about interference. So constructive and destructive interference. How do waves interact with each other? This is a very important idea in any sort of wave mechanics. So this has applications to light. It has applications to pretty much anything that has periodic functions involved. Okay? All waves behave in the same way when they interfere with each other. The way they interfere is really quite simple and really quite powerful. Okay? When we talk about wave interference, all we're saying is that the waves add to each other. Really, if you have two waves in the same medium, they interact with each other by acting on the particles of the medium at the same time. Basically means they push each other together. Let's consider this wave here. Let's imagine a spot here. Let's just pick any random spot here. Let's think of this wave here. This has some let's call it y1, which is a sort of the amplitude there, but it's also the y value, the amount of extension we have in the medium at that point. Okay, at the exact same point, if I follow it along here, I get to another point on this red wave, which I've just transposed the red wave up a little bit so we can see everything. But this has a y value, let's say y2, that. Okay, so it's being pushed by that certain amount up. When we add them together, which is this wave down here, I'm going to end up with, at that point, extension, which is just going to be exactly equal to y1 plus y2. They just add up directly. Waves just stack on top of each other. And they end up doing very interesting things. Like this wave here shows the superposition, we call this, of these two waves. This longer frequency one. This one has some sort of wavelength here, call it lambda 1, whereas this one has a much longer wavelength, which is lambda 2. So you can see in the superposition of them, it shows sort of an envelope from the larger wavelength wave, and then it's going up and down according to the shorter wavelength wave. So this is the sum. We call this, let's call this y of t, y2 of t, the bigger one. This other one can be some function of y1 of t. The sum here is y1 of t plus y2 of t. We just add up directly, and it works perfectly. Okay, so that shows us the sum of those two waves. The sum, the superposition, the interference between the two of them, all those terms. Okay, so let's break this down a little bit more carefully. So when we look at these waves, let's say we have two waves that are coming together, right, in the same direction, and they have the same amplitude. They both have an amplitude of this. Okay, there's the one, and this one has an amplitude as well. And this both in the same direction. They're both positive, we can say. Which means that when they get together in the middle, they end up having an amplitude which is twice that. This is, let's call this A, let's call it A, this is 2A. And we end up having what we call a supercrest. We end up doubling the amplitude of the wave where they meet together. Okay? So this is called constructive interference. They build onto each other. They increase their volume if it's sound. Okay? Or they just get bigger if it's water or something. The complete opposite happens if one of the waves has a negative amplitude. Let's say I have the one here that has an amplitude like that, and the other one that has a negative amplitude. What they're going to do when they meet in the middle is completely cancel each other out. These two waves, when they meet, their amplitudes, right, because A plus minus A plus minus A is just going to be equal to 0. Negative A, A, we end up with 0 in the middle. Okay, this is destructive interference. Waves are able to cancel each other out, and you can have quiet spots. If you fiddle around with a certain geometric shape and a certain frequency in the sound, size of a room, you're able to actually cancel out sounds. You can have dead zones. Okay, or you can have spots where waves get louder. You can have what we call a bass trap, where there's too much low end being sort of concentrated in one spot in a room, or you can have spots where stuff cancels each other. These are out of phase. Remember this is the term out of phase. They are opposite each other and cancel. Okay. What's really awesome about this now, it means that any wave, any sort of complex periodic function, can be made out of just a sum of waves. Right? We can put together, for example, here I have a 100 hertz wave, 200 hertz, 300 hertz. That means these are going up and down every 100 times in 1 second, 200 times in 1 second, 300 times in 1 second. These are probably sound waves. And they're going to come up with this complex function. The fact that you can hear me, the sounds that I am making is made up of a huge sum of different waves all together. And we're able to interpret all of those separate frequencies as they vibrate, as they go up and down, as the air goes in and out. We're able to interpret that as sounds. Okay? So because of this idea of what we call Fourier analysis, that I can just make up an infinite sum of these things. It doesn't necessarily have to be infinite, but most likely infinite, we can come up with any wave. We can do all kinds of complex things, even things like a square wave, something that you'd imagine is impossible to make out of waves. If we have an infinite sum of these, notice these are all odd, these are all odd wavelengths. Right? This is the full wavelength here, and this is a third, a fifth, seventh, and you keep going. If I add up an infinite number of those, I'll end up with a square wave. This is a funky way of showing it. These are called epicycles that show how you can build these waves on. So we have our original wave, which is made up of the, what's it look like? The y component of this radial arm. There's some sort of y component right here. So as this is going around, it's showing us the y component. So now I'm going to add to that a faster wave. In fact, a third of, sorry, 3 times as fast. So every time this orange circle goes around the circle, the green circle is going to go around 3 times. We put that together to look at the y value. We come up with this sort of basic approximation of a square wave, but we can do better. Now we're going to add to that a circle that goes around 5 times, or add to it another circle, this red one, that's 7 times. And we look at the y component here, and we can see it's going up and down, and it's getting closer and closer to a square wave. If I added up an infinite number of these, I can come up with a square wave. And the reason we care about square waves is square waves are very simple electronically to produce. The voltage is on, the voltage is off, and it does that in a periodic fashion. Okay, so we can come up with this square wave, which we can do electronically, something just on off in some periodic fashion. We can actually come up with a mathematical formula for that by being an infinite sum like this. Okay? Here you can see it when we go up to n equals 15. We get closer and closer and closer. And the epicycle shows us how this works. Okay? Again, we're looking at the y value. Which is pretty awesome. Now if n approaches infinity, here, n approaches infinity, our wave will actually become a square wave. All right? So this is a very, very quick introduction to Fourier analysis. Fourier analysis is something that you can take entire courses on university if you'd like. Signal theory, how we produce these signals, how to get rid of noise in signals, all that sort of fun stuff. Okay, here's another nice picture of showing this. These are 5 different waves. The other thing is the amplitude. On this side, this shows us, inside, this shows us all these different waves. And these are adding them all up. And then this is the amplitudes of each of them. Notice that's the size of the circle. Think of it as the size of the red circle is equal to, like, there's our red circle. And we have our, what's the next color in our picture here? It's blue. This would be our blue circle, and so on and so forth. And that's the size of them. And that represents how much influence this has on our final wave. Okay? So it's a very powerful tool in analyzing any sort of waves. And unfortunately, the math is well beyond any high school stuff. So just to give you an idea of basically what it means to come up with any wave from a sum of simple sine waves. All right, so very quick lesson, only 10 minutes so far. All I want you to do is, there's 2 practice pages on the Weebly. Right, one of them has 3 pages, so altogether 4 pages. Print them off and let's see what happens when we draw some pictures of waves actually um, interfering with each other. So in the first one, it's a triangular pulse, and you can move it along these little dots on the paper, and you can see what happens as they add up together. The other one is actually drawing sine waves and then adding them up using the superposition principle that we just literally add the value of the y's together, come up with a new wave. Okay, but before we do that, let's quickly go to, where's Desmos? Here's Desmos. I'm also going to put this on the Weebly. This will let you play with some of these ideas that show the same thing. So I have a red wave and a blue wave. Let's hide everything for now. Okay, so here's my red wave, and these little sliders allow me to control how big it is, the amplitude of the wave, even negative. But it lets me adjust that. And I also have a K, which allows me to adjust the wavelength. We call this the wave number. The larger the wavelength, the larger the wave number, the smaller the wavelength, right? So we can increase the wavelength. And I have a second line here. I'm going to call this Y2, and we can add them together. All right, and you can play around with this and see what happens. Let's use the blue line. Let's make the blue line larger. Have a smaller red line, but we're going to make it very, very fast. Okay, so this actually shows us how radios work. Radio waves work by having very long wavelength electromagnetic radiation. So they're called radio waves. They're very long wavelength, in the order of tens of meters, hundreds of, which means they can travel very far. The longer the wavelength means it can travel through buildings. You have no problem picking up a radio wave inside your house. Granted, if your house is a big metal box, you're not going to pick up anything, and then the whole house will be a Faraday cage that stops any electromagnetic radiation. But long wavelengths have no problem getting through wood and that sort of stuff. And on that long wavelength, we put a much, much, much higher frequency wavelength. That is the actual signal that we want to hear. That's the actual audio we want to hear. Or you can do it back the other way around. So for radio waves, it actually works the other way around, where the carrier wave is much higher frequency, and then we put them together like this for what we actually want to hear. This is the sound wave that you want to hear, and this would be the radio wave. Sound wave is much longer. We can put them together and come up with our. Now this would be an example of AM radio. And notice if you look on a radio dial, there's amplitude modulation and frequency modulation. Amplitude modulation is just this, where we add them together. Frequency modulation, we change the frequencies a little bit more complicated. Get much better signal. You're able to actually produce stereo signal, have a left and a right speaker. But this is getting a little bit too complicated. Let's not worry about this. I've gone off on a tangent. I apologize. Okay, so here I'll let you guys play with this. You can see how the different waves interact with each other. Right? You can play with different amplitudes, and I've even got a different one on here as well. What is it? This one here. And I'm also going to put on. It lets us have 3 different waves. So the green wave is representing the sum of these 3 different waves, and you can play with the amplitudes and wave number of the different waves and see what happens. And if you go and press on the C, it actually will travel. Okay, and you can even change the plus or the minus. The waves can be traveling in opposite directions and be doing some more complicated, more fun things. But this one has a plus. This will all be traveling to the left. See some complex interactions here between all those waves. Okay, so I'll put all these on the Weebly. You can play around with the wave superposition, and hopefully that helps. All right, so that's all for now. I hope you guys are having fun. I hope you guys are doing lots of physics, and staying up to date with all the work that you have in your other classes. I know this is a trying time. I hope you guys are just doing your best. I hope to see you sometime before September, but who knows. All right, so best of luck, and stay safe.